I'd like to thank you for coming in because by a show of hands, you all know complex numbers certainly well enough for this class. But I'm still happy to be able to talk about complex numbers. I didn't think everything through in detail what I want to talk about today, but I want to give you sort of an arc of the subject of complex algebra, not complex analysis. There won't be any derivatives with respect to complex variables, just complex algebra, which is a phenomenal subject, an amazing invention in mathematics, certainly of central importance to this class, central to virtually all topics in applied mathematics. And to explain the importance of complex numbers, you just have to mention two things. First, doesn't sound like a big deal, but it proves to be the biggest deal in engineering and elementary, basic, fundamental applied mathematics. And that's marrying trigonometric and complex functions. And of course, that's done with the help of Euler's formulas. Euler's formula, considered one of the most beautiful equations in mathematics, and deservedly so. And that's part of the reason why I was looking forward to talking about this, because you get a chance to talk about Euler's formula. And maybe even more exciting is a chance to talk about Euler, to whom we owe a debt of gratitude for everything that we enjoy in mathematics today. There is certainly something to be said about Archimedes, maybe a whole lot to be said about Archimedes, and Descartes, and Newton, and Leibniz, but it's Euler who was, number one, just an amazing human being, amazing person, and also turned math into the subject that we know today. All of the notation of his, all of the aesthetic is his. Not to say that the greats before him and after them didn't have aesthetics. They all did. They all had incredible taste. But I believe that imitating Euler is one of the great ways to study mathematics. And he certainly gives us a lot to imitate. And his writing was extraordinarily generous. He wrote false paths and his emotions and how he felt about a certain subject. And he was, at the same time, humble and combative and didn't hold back and attacked his intellectual enemies and really argued his point and without any hesitation admitted weaknesses of his point of view. And it's just a fascinating example to follow. And complex numbers give us that opportunity. But in terms of the importance of complex numbers, Euler's formula and the marriage of trigonometric and exponential functions is so important. It makes cumbersome things so simple. And the other application, which I think a math major would mention first, and deservedly so, is the fundamental theorem of algebra, which states that every polynomial of degree n has exactly n roots, which is not true if you don't have complex numbers. And I don't even want to think about what would fall apart if we didn't have that fact. There's certainly a fact if you limit yourself to real numbers, proved by, you guessed it, Euler. And that's the fact that if you have a polynomial of degree n, it can always be factored into quadratic polynomials. That's a theorem that exists and was proven by Euler without complex numbers. And that's almost the fundamental theorem of algebra. Because each one of those quadratic polynomials, you can either find its real roots or its complex roots. And that shows that they're exactly n. We know very well there cannot be more than n, because you could multiply the factors together and you would end up with a polynomial of degree higher than n. That's details. Okay, but with complex numbers, that statement becomes a blanket true statement that's always true. That a polynomial of degree n with real or complex coefficients has exactly n roots. And I have actually never stopped to think how this fact permeates all of mathematics. When we talk about eigenvalues, when we talk about other related problems, we kind of take it for granted, and I don't know what would fall apart if we didn't have it. So that's like, if, you know, we live in an age where you have to motivate everything that you do. And that certainly motivates complex numbers. You don't need two motivations, but we have two, and that's great. So that's why complex numbers are important. But I think that complex numbers are even more important to study because they teach us so much about mathematics. They teach us about the tortured path that mathematical ideas need to follow in order to be accepted. It teaches us how we have to accept absurdities. And there were people before Euler who sort of embraced complex numbers which clearly didn't exist. After all, we will be talking about the square root of -1, although we'll try to never write something like that, because that's nonsensical. It's absurd. But some people got this sense that even though it's absurd, it exists in this other ghostly dimension where it has a right to exist even though it doesn't make sense. And that could go for a lot of mathematics. But it took someone like Euler to see the full breadth of the usefulness of this absurdity and how everything connects and how everything makes sense and how nothing's contradictory and therefore is perfectly legitimate. So we'll get back to that. But it teaches us to embrace absurdity. It also teaches us the power of imagination. When we study math, maybe early on when we're younger kids and we try to solve those fun problems on Putnam exam type things, math Olympiads, we're presented with these things where we have to use our imagination. If we study geometry, which we don't do as much anymore, we use our imagination. But then there are other forms of imagination where you just go on these incredible journeys and you say, I'm just going to imagine this and it's gonna work. And so I would say, in my experience, this is one of the primary examples of the use of imagination in mathematics. And once again, in a way following the example of Euler, but other great mathematicians as well. And it also teaches us that we could have easily missed things. It's amazing what people miss, what generations of incredible mathematicians miss. One of those stories actually involves Euler and his famous polyhedron formula. You know the formula that the number in any solid, the number of faces, edges, and vertices satisfies a formula where there's a 2 on the right-hand side. And you would think solids, the ancient Greeks would have gotten that elementary relationship, but no, they didn't get it. Everybody missed it. It came to Euler, and he didn't miss it. He didn't miss much. That's another nice thing about Euler, is that if you know that if you worked on something, that it was pretty much completed. And since we're on the subject of algebraic equations, I'll give you another anecdote, and then I'll continue with my point that it teaches us how easy it is to miss things. But quadratic equations were solved by the Babylonians. Cubic equations, I have a formula, a cheat sheet, will play a prominent role in this narrative, were end of 15th century, maybe 16th century. Quartic, fourth order equations followed soon after. It was the same gang of people who pretty much figured it out. And then the quintic, the fifth order equation, they couldn't do. And then Euler, 200 years later, was still preoccupied with the quintic, with the fifth order equation. And he wrote a paragraph that said, I've worked on this problem for a long time. I've tried this, this, and that. And whichever avenue I followed, I eventually failed, which makes me wonder whether solving the fifth order equation can be done at all. And only 40 years later, it did require new blood. Interestingly, Euler didn't do it. It required a couple 20-year-olds, Galois in France and Abel in Norway. They both died in their 20s, I believe, who proved that there is no such thing as a formula for the fifth order equation. So Euler's inkling was right, even though he couldn't show an argument for why that's true. This next generation of great mathematicians kind of had a very important clue that this person did everything he could and couldn't do it. So maybe it's impossible. Okay, but Euler did miss that. And Euler missed another thing. I don't know how it escaped him, but the fundamental theorem of calculus has a very elementary, what did I say? Fundamental theorem of algebra, which is the fact, I don't know if I've already said calculus instead of algebra several times, so I'll just use them interchangeably. When I say fundamental theorem of calculus, I mean fundamental theorem of algebra, that there are n roots, has a one-line proof. I'll prove it to you instantly. And that proof is relatively recent, and I don't understand how Euler could have missed it. And then there are other amazing things of what people missed. There's an anecdote, I don't believe it at all, that Descartes, again, it's related to polynomial equations and factorization, that Descartes looked at this polynomial and said it couldn't be factored. That this is an unfactorable polynomial. You cannot factor it into quadratic polynomials. And of course you can. Of course you can. You just have to add 2x squared, and then this becomes a perfect square, right? If I add 2x squared, and then subtract 2x squared, and here I have a perfect square minus a perfect square. It's a difference of two squares. Of course you can factor it. You can see what it ends up being. X squared minus square root of 2x plus 1, and x squared plus square root of 2x plus 1. So the story goes that Descartes missed it. I've never seen it in an original source, so I don't believe this anecdote, but it does exist, the anecdote. And then there were, this went on, and there was a letter to Euler. I'll show the slide where a collaborator of his wrote, well, this we can factor, but here is a fourth order polynomial that you cannot factor. I've worked on it as much as I could, and I say, this you cannot factor. And a couple weeks later, Euler replies, here's a way to factor it. And it's an expression that will barely fit on a slide, and then he explains how he did it. And I never read that, so I have something to look forward to. Okay, so things, elementary things can be missed easily. Beautiful things can be rejected. Hard to be accepted. Easy, obvious things are missed. So what are we missing now? That's a good thing. So it kind of shows you that these beautiful mathematical facts are all around you, and the ancient Greeks and Descartes and Euler could have all missed them, and they're still for us to find. So don't give up. Don't be intimidated. Those people are our friends. They left us things. And finally, I don't know how this fits into my whole spiel, but now that I feel talkative, I'll say that I think all of this shows that the public perception of mathematics as being this absolute, perfectly structured subject that's waiting to be discovered is totally opposite of how it is. Mathematics is the most personal, the most individual, the most emotional subject where your personality, maybe even more so than in music, I don't know, comes through in what you do. It's opposite of the dry, nerdy, emotionless, cold subject that the general public perceives it to be. It's the exact opposite. It's the most emotional thing here. You have to be angry at square roots of -1. You have to feel like you want to conquer them. You feel like you're in a battle, you're going to get it. It's hiding from you. God is hiding it from you. You have to defeat greater powers. It's just, that's what math is. And I think complex numbers teach us all of that. All right. So now I've built it up, and now I'm not sure which way I'm going to take it. But here it is. Let's agree that the square root of -1 is absurd. I'm going to write it again. But we know that if you take any number and you square it, you get a positive number, or 0. But if it's not 0, it's a positive number. 7 times 7 is 49, but -7 times -7 is also 49. There's no way to square a number and get a negative number, in particular -1. So right again, we begin with a premise, with a symbol that makes absolutely no sense. Let's just agree on that. You cannot accept it. I submit that if you look at this and you say, I accept it, you're a better person than I, I just don't see a path where you just say, okay, I'll just work with it. You can't just work with it. So Euler made a very important step. So I'm going to do it all out of sequence. He gave this a symbol. He called it I. I is for imaginary. As you know, Euler named all the numbers that we use. He used E for exponential. He used pi for perimeter, or I think something else. So E, pi, I are all his choices. But I is for imaginary. Well, let's think about I. So I squared equals 1. Excuse me. I squared equals minus 1. Okay, so he says, well, we know that the square of any number cannot be negative. So I cannot be positive. I cannot be negative. I cannot be 0. I cannot be any number that we know. It's only a number that exists in our imagination. So I will call it imaginary. So that's where the term was used before. But when he used the word imaginary, he did it in a very, very positive way. There were people before him, maybe I'll have a chance to talk about it and share with you everything I know, which is from other sources. The people who called these numbers imaginary, meaning absurd and to be rejected. When Euler used the word imaginary, he meant it to be embraced. And one nice thing he did was, instead of writing square root of minus 1, which he did also, but by inventing I and writing down this relationship, he was laying down the foundation for accepting complex numbers, because that's already an algebraic rule, and ultimately that's what makes complex numbers work. They don't exist, but you can operate on them as if they do. And then you can almost get used to them because they produce interesting results. So we'll talk about that also. So doing this allowed us not to write the square root of negative 1, which is problematic for so many reasons. Tangible reason, which I wrote down on the board last time, and I'll write it on the board again. So this was an important step. It says, let's use I as any other algebraic letter and write that it equals minus 1. And that's laying down the foundation for the algebraic approach to complex numbers. Algebraic meaning that, well, he says they're imaginary, so just imagine that they exist. I could have never done that, especially given my training of epsilons and deltas and real analysis and piano postulates and Euclid, where everything starts at a clear or so you think point and then you move forward. I can never accept, I can never say, imagine that something that doesn't exist exists, and let's see what we can do with it. So I think that's a very important lesson, that sometimes you just have to do it. Sometimes you just have to do it. What makes it easier to do it? If you're just starting out and somebody tells you, imagine that 5 equals 6, and let's just see where that leads us. If it doesn't lead anywhere interesting, it's just going to be a very boring conversation. But if it actually leads to something very interesting, then you'll be like, I'm going to give this a second thought. And in the case of Euler, you could see not just one place where it leads to something interesting. Euler could see 2,500 different directions in which this absurdity, if you just follow the rules of algebra, ends up working. Okay. So that's the point of view that we'll adopt right now, even though there are alternative points of view, and I'll mention that also. That let's just use this symbol as we would use any other variable, and whenever we see I and terms involving I, we'll combine them as like terms. And whenever we see I squared, we'll just write minus 1, and then we can work with algebra. And then you realize, and I'll show that, and then I'll show more, that you can now all of a sudden solve quadratic equations. But what does it mean, solve? Well, maybe it's time to do that. But let me first write down the rule. The rules. So here says I is imaginary, doesn't exist, but let's work with it as if it does. So do that more often than you feel comfortable to do that. Do that, because that's how delta functions are are constructed or embraced. You're familiar with delta functions? Yes, physicists? Delta functions, they don't exist. It's a function that doesn't exist, that equals 0 everywhere except at one point where it equals infinity and its integral is 1. Total nonsense. Right? So they don't exist. But pretend that it do and just proceed using the rules of algebra and see what it does. You just have to be able to do that. You have to embrace something that's absurd and just see what happens if you accept it. And great things will happen. So the rules are a plus bi, so we're now considering them in linear combinations. Can I use that term with real numbers? Here's how Euler would write it. Plus c plus di. And I don't even need to write down the rule. It's a plus c. You don't need parentheses. I'm just grouping them. Plus I, b plus d. Okay, so something that doesn't make sense we're now working with. Okay, great. Of course, interesting is multiplication, where a plus bi times c plus di. Let's see, it's ac minus bd. I don't need to justify it, right? When you multiply it out, you'll have AC, you'll have BD times I squared, which is minus 1. Those are rules of working with these nonsensical things. But you know, other things are nonsensical, and we're okay with them. Don't let me forget to talk about negative numbers. Okay, times, what do we have in here? AD plus BC. AD plus BC. Is that right? It's AD plus BC? Did you ever realize that you get two errors in parentheses as the imaginary part? You know, this is before Christ, and isn't that amazing? Have you ever noticed that? I've never noticed that. That's pretty cool. This is positive and this is negative. That doesn't make any sense. Okay, but that's kind of cool. Okay, so these are the rules. And then you proceed, and then I'll show you in a moment that you can, quote unquote, solve quadratic equations. So I'll do that in a moment. We'll solve quadratic equations, and then we'll reject it as a useless thing. And then we'll move on. But first I want to say that there's a long history of mathematicians struggling with things that don't exist, and then eventually accepting them for their utility, and then getting used to them to the point that you don't even question it anymore. And a primary example of that is negative numbers. So negative numbers don't exist. You cannot eat minus 2 apples, right? You cannot, your salary cannot be minus whatever, and on and on and on. Right? These numbers don't exist. So how did we end up with negative numbers? Well, that's because we would metaphorically extend or algebraically extend things that do make sense. So we would solve a problem like that, like the following. I have 5 apples, and then you gave me a few more, and now I have 8. How many apples did you give me? And the answer is 8 minus 5, 3 apples. You agree with the math? Now suppose I have 5 apples, and you gave me a few, and now I have 2. Okay, well that doesn't work, because you can't give me apples and then for me end up with fewer apples. You agree? And there is no such thing as giving somebody minus 3 apples. Now, of course, all of you will say that giving somebody minus 3 apples is the same as taking 3 away, right? That's true, but that's because you've gotten used to it. That sounds incredibly nonsensical, to give somebody minus 3 apples. You understand, right? That makes no sense. We kind of get used to it in certain situations. And there are 2 reasons why, number one, it started happening, and then why we accepted it. It started happening because we would solve a plus x equals b, which is the problem we just did, and the solution is x equals b minus a. And then you start thinking, as a person of algebra, I think before algebra, this couldn't have happened. And algebra in European science is a recent phenomenon, 16th century, maybe 15th century, right? Compared to ancient Greeks, which did 90%, I don't know, of what we know. I don't think they could have done negative numbers because they didn't have algebra. It's really writing this down and then saying, well, what if this is 2 and this is 5? Maybe this could still be endowed with meaning. And so you will notice that we kind of started doing that, and then the world didn't come to an end, even though we ended up with 2 minus 5 equals minus 3. Because we have to accept the fact that in mathematics everything is imaginary, and you can kind of suspend your judgment, right? That's also what it is a matter of, your preconceived prejudices. Sometimes you just have to suspend and say, okay, minus 3, you can't have minus 3 apples, but I can write minus 3 and my computer won't crash, right? Or my piece of parchment won't explode, right? So you can do it, so it's okay. So let's see what you can do with it. Let's see if we can tie these objects into our algebraic framework. And it worked out. And there were no contradictions. And they were slowly accepted, but more recently than you would think. So Descartes would call these numbers, I forget the word, absurd, non-existent. If he solved the quadratic equation, or any equation, and it had a root of minus 3, he would call it a false root. And he wasn't a dumb man. He was a very, very smart person. I'd swap intellects with Descartes anytime, even if he wouldn't accept complex numbers, negative numbers, okay? So this was, in its own way, a tortured path, much more tortured than with complex numbers. It took many more centuries to accept negative numbers than it did to accept complex numbers. Okay, so all of the rules of algebra worked, but even more importantly, you should note that the final answer is never minus 3. We do always pull our answers back to reality. If I owe you minus $10, it means you owe me $10. By the time a physical transaction or a physical action takes place, it's always with positive numbers. I cannot take minus 5 steps in this direction. I can take 5 steps backwards. Right? There's that backwards component, but when I'm taking steps, I'm actually taking 5 steps. So that minus sign always gets interpreted away. And by the time it comes to a physical transaction, the negative part needs to go away and get translated into something that makes sense. So when it comes to money, the negative sign means that the transaction needs to happen in the opposite direction. But then the transaction is still with your pieces of paper or coins. It's still a positive, real transaction. So negative numbers, which you accept, all of you accept without a second thought, make just as little sense as the square root of minus 1 or something like this. It doesn't exist, but just because it doesn't exist doesn't mean that we can't manipulate it algebraically. We can, and we will, and we'll see where it takes us. Now, let's use this I to solve a quadratic equation that doesn't have a solution. And then I'll criticize it, and then you'll see where it actually came from historically. So let's pick an equation that doesn't have a solution. X squared minus 4x plus 13 equals 0. Pretty good. I always think of 2 plus 3i. Seems like a good combination of numbers. But let's sort of get there. So first of all, you can make sure, if I just wrote 2 plus 3i and 2 minus 3i, then by using these rules, you could plug both of these in. Did I do it right? I think I did. Yeah. You can plug them in, use these rules written down, right? Nothing makes sense because it doesn't exist. But the rules of algebra don't care that I doesn't exist. It can still manipulate I even though it doesn't exist, and you will get 0. Whether you plug this in or whether you plug this in, you'll get 0, so it has 2 solutions. So in that sense, hey, complex numbers are a positive step forward. And you would say, no, it's not, because this is just another way of saying that the quadratic equation doesn't have any real solutions. That's just another way of saying it. By saying that the solutions are something that doesn't exist, That's just another way of solving it. Let me get to that point in just a moment. But first, I want to show you that the quadratic formula does give you this. So 16 minus 52 is minus 36. Minus 36, we have to be a little bit careful because we didn't talk about square roots yet. That's a big discussion. But this will end up being 2 plus or minus 3i. So the quadratic formula kind of gives us these answers. We don't have to guess them. There's a square root of minus 1, which I kind of rejected outright. But you can discuss all of this without having a square root of negative 1. You'll just flip signs and put in i's when necessary. This talk is not about details. But, again, if it was just quadratic equations, if it went no further than this, this would be an idle exercise worthy of being rejected. It's whether or not you can do something useful with these, right? Because if this is the final answer, remember, the final answer can never be a complex number. So, not a good motivation for complex numbers. And historically, this is not where complex numbers came from. You need to take it a step further. And you'll see, and especially applicable to ODEs, it will be Euler's formula that takes this a step further and makes it useful and gives you back real answers, real values. So here's how complex numbers came up historically. I might actually be able to give you a specific equation. And you will see that in there was a germ of usefulness. And it having enough of a payoff that people felt compelled to accept, not people, one person, Bombelli. They said, you know what, I'm just going to stick with it. Makes no sense, doesn't bother me. So, quadratic equation, Babylonians. Cubic equations, I'm going to mess up my century. I want to say early 16th, mid-16th. People started solving the cubic, and they realized that all they have to do is this. So you see the quadratic term is missing. Any cubic equation, by one clever substitution, you can kill the quadratic term. In fact, in any order equation, the same substitution kills the next order term. So you can always, by one substitution, remove this term. So they did it for the cubic. And then Tartaglia of, I forget what city he was from. Tartaglia, which means stutterer. He suffered an accident as a kid, like something went into his throat and he stuttered for the rest of his life. He had a very complicated life. But in any case, discovered the formula, told it to Cardano. And Cardano is a name you guys don't know, but he should be celebrated as much as Leonardo da Vinci, maybe more than Leonardo da Vinci when it comes to matters of science. Certainly right up there with Galileo. Was the premier doctor, was probably a poet. Just a true Renaissance man that no one has ever heard of, but he deserves all the credit in the world. Well, in any case, Tartaglia told him the formula. He published the formula. He credited Tartaglia. Tartaglia was still unhappy. And the history of how these formulas were discovered were just amazing. It became a fad to solve polynomial equations of higher order. And so there were stories of duels, mathematical duels, where two mathematicians would exchange equations and see who could solve more of their opponent's equations. And that certainly was, when there's excitement of that caliber, beautiful things happen. And so they discovered the equation for the cubic, then for the quartic, and then they broke their leg on the quintic for reasons that it didn't exist. But in any case, the solution is, I'm actually going to write it out because we're going to work with it. So here is, it's called Cardano's formula, and it looks like this. And you will see that there's some elements in it that are reminiscent of the quadratic equation. But of course, there's a cubic root. I guess what I should have done was right before I did this, I should have just memorized this, and then you would be totally impressed. But I don't remember this formula. Tartaglia's or Cardano's formula. At the time this formula was invented, the language with square roots and this for the square and this for the cube and this for the cubic root was not developed. That came later. So they actually struggled writing this formula in this way. So Tartaglia wrote it down in the form of a poem, and actually a beautiful poem.
Quando che il cubo con le cose appresso, se agguaglia a qualche numero discreto, trovan due altri differenti in esso. Da poi terrai questo per consueto, che il lor produtto sempre sia uguale al terzo cubo delle cose neto. È il residuo, poi suo generale, degli lor lati cubi ben sottratti, varrà la tua cosa principale.
There are lots of other details to share. So let's use this formula to solve a couple, and that will actually, we have to do some algebraic work, don't we? So the first equation is x cubed plus 3x minus 4. This will prove somewhat uncontroversial. Can you guess one root? 1. Plug in 1. You get 0? Yes. But when you use this formula, you get this. You get this formula. Okay, let's see. Cubic root, c is what? C is 4. So you get 2, right? Yeah, 2. Good. Cubic root, 2. Now, b is 3. So this is 1, and this is 4. 2 minus square root of 5, yes? So we know that the root is 1. We should graph this to see if there are any other roots. Of course, that question is always present. Is it one root or is it many roots? Okay, but this is, so does this equal 1? Yes, it does equal 1, but this puzzled them, right? This will puzzle you because it's kind of great to revisit the sorts of, you always think that it's these high-flying ideas, but sometimes it's working out the details. Not sometimes. I'll bet you it's always working out the details that puts you on the path to great inventions. So they're like, all right, they probably estimated this numerically, and like, that's 1. But it's really hard to see that it equals 1. So how do you see that it equals 1? Well, they said, okay, well, here's one thing I know. And we're going to actually delve for 5 minutes into group theory. Because what they noticed is if you have a number of the form a plus square root of 5b, where a and b are rational numbers. So do you see this as a subset of real numbers? Numbers of the form a plus square root of 5b, where a and b are rational, and square root of 5 is irrational. If you take one number like this and you multiply it by another number like this, will you get another number of this form? Well, when we multiply it, here's what we get. We get, I'll put parentheses just to group things. Do you guys agree with this? And so you notice that, oh, that's very interesting. When I multiply numbers of this form, I get another number of this form where it's irrational plus irrational times square root of 5. So there's closure under multiplication. There's also closure under addition. A sum of two numbers like that is clearly another number like that. Do you see that it's a structure similar to complex numbers? I wish I hadn't erased it. It's just that instead of I, where I squared equals minus 1, so I is out of the set of real numbers. In fact, it's in the imaginary domain. But I squared is right back where we want it to be. The same way square root of 5, it's out of the realm of rationals. But by the time you put square root of 5 and square root of 5 together, that brings it back into rationals. So do you see how in terms of algebraic structure, this totally tangible example by our standards algebraically is identical to complex numbers. Totally identical in the way closure works out. There's another thing that you can do. You can even divide. We haven't even talked about that. I keep erasing things that I should have left on the board, but you can talk about what 1 over a plus b square root of 5 is. Even that becomes a number of the same form. How do you do it? You multiply by a minus b square root of 5. Isn't that a brilliant trick? You multiply it by a minus b square root of 5 on the bottom, and correspondingly, oh, what did I do? On top, a minus b square root of 5. Do you see that's the standard? Everybody knows this and knew then. You can always get rid of the radicals on the bottom. You can always find something to multiply them by so that the radicals on the bottom go away. Ooh, hopefully this is not 0. It can't be, right? It could be. It can't be. It can't be. If this is rational and this is rational, this cannot be 0. Or can it? It can. Yeah, no, you can. Okay, well, think about it. Suppose it's not. I think there's a problem here. I think this will not quite be what's called a field. Because for some numbers, if b, no, it would. I have to think about it. A and b are rational. Remember, if they were integers, this couldn't be the case. But if they're rational, no, still can't be the case. No, we're good. If they're rational, this cannot be 0. Because if this is 0, then square root of 5 is rational. We're good. It's a field. Because we're closed under addition, we're closed under multiplication. Every number has a reciprocal. And of course, all of the other laws such as associativity, distributivity, all of them work. So these numbers, a plus square root of 5b, I already erased them, form a field under common multiplication and common addition. That's kind of beautiful. Okay, but can you take cubic roots and hope that there is it's another number of the same form? So that's what the hope here is. The hope here is that the cubic root of this is another number of the form a plus b square root of 5. A plus b square root of 5. That's the hope. Right? Because look, it's all full and nice and closed and everything works in terms of multiplication, addition, and the reciprocal. Well, maybe cubic roots will work also. And how would you find out? How would you find a and b? Well, you'll cube both sides, right? You'll cube both sides. You multiply this out. You get another number of the form a plus b square root of 5. And then you say that should we call it real and imaginary? That doesn't work. How about normal and radical terms? The normal terms, you'll just, whatever, you multiply this out, you'll get something without the square root of 5, you'll equate it to 2. And then something times square root of 5, you'll equate it to minus 1. And you'll have a system of equations with 2 unknowns and 2 equations, a and b. And it will actually have a solution. I don't remember what it is, but I'm sure a is 1/2, and b, I think, is minus 1/2. I think that's 1/2 and minus 1/2. And so this ends up being 1/2 minus 1/2 square root of 5. Okay, that's what he figured out. So he extracted the root in the same form. It turns out that you can't always do that. And so these numbers are not complete in that sense, that you can take cubic roots and still get a function of and still get a number of the same form. So there is a flaw in these numbers from that point of view. And then similarly, fantastic. You add them together, The answer is 1. So the formula worked. It just required this extra work. That was good. Then came the next equation. Now you guys, can we declare a victory on this one and move on to the next equation? And so we're sort of retracing Bombelli's steps. What's one of the solutions? 4, right? Just plug it in. So he knew the answer would be 4. But let's see what happens according to Cardano's formula. Equals. Good. So 121 is a perfect square. Let's acknowledge that. So Bombelli came across this, and anyone else, or depends on your personality, I guess I'll speak for myself, and I would have just become dejected and quit the whole thing because my formula, in some cases, my formula works beautifully. In other very similar cases, my formula doesn't work at all, or somebody else's formula, so I would feel bad about mathematics. You know, it should be pretty, but it's not. Greeks could keep it beautiful. I'm just a post-Middle Ages European. I'm not as smart. I can't do anything about it. I give up. That would have been me. Okay, but he said, okay, let's see. I'm now going to start considering, right, the algebra, my piece of paper doesn't explode if I just algebraically follow the exact same procedure I just did with the square root of 5. Right? Let me just, what's the word? Plow my way through this. Suspend my sense of absurdity because algebra still works. And just plow through with this. And I will just say, hopefully the cubic root of 2 minus 11 times square root of minus 1 also has the form a plus b square root of minus 1. And then this would be, if this was the final answer, nonsense. But then I know what happens with the square root of 5. Maybe when I do the other part, right? See, they come in pairs. Clearly, this would be, you know, by all the symmetries that I have observed, it would end up being a minus b square root of minus 1. And when I add them together, just like the square root of 5 dropped out, leaving me with a beautiful rational, maybe this will drop out. In fact, I know it will because I've done enough examples with the square root of 5 that I know all of the algebraic patterns that will play out. And I'll just end up with 2a. That was his hope, and it exactly worked out. He did the exact same thing. He cubed both sides, matched up the parts without the darn square root of minus 1 and the parts with the square root of minus 1. You see, he was a doer. So he just did it. And then the a was 2. He solved it. A was 2. B, I don't remember. But it doesn't matter because that canceled, and you were left with 4. And so he said, maybe there is something there. Right? There's not anything there from the point of view of making sense. But there is something there in the sense that formal algebraic steps survive. You know, we do it now often with computers. Right? We do some kind of, I don't know, a specific example. It feels like I would have many, that we develop some kind of filter for some kind of purpose. And then we plug in the totally wrong thing and totally unexpected thing into that filter, and we get a totally unexpected result. And it's fun, right? Because that filter wasn't meant for our input, but it still works. It doesn't make sense to put our input through that filter, but we still do it, and the outcome is fun. Except in this case, the outcome is glorious. So he said there is something there. So let's just do it. Let's just write down these rules, and the rules like you saw, with that as if it exists, presuming it exists in some form, presuming it makes sense in some form. The rules pretty much write themselves. Let me repeat them. And you know, this happened before Cardano wrote his famous text. I forget what it's called. Ars Algebraica or something like that. The Art of Algebra or something like that. He gave this very example. And he made a very interesting pun. He said, he called this, it was written in Latin, and it could be translated, I spoke with a classics professor about this. It could be translated in two different ways. One of them, he said, we do this algebra, and then he said, dismissing mental tortures, we arrive at the answer of 4. And that's the common translation, if you pick up that text, because that's the more romantic translation. Dismissing mental tortures. But it could have also been imprinted, instead of the word dismissing, it could be the word canceling. And mental tortures, it was the same word as cross-multiplied terms. Does that make sense? That crossing and mental tortures would be related words? So it was either dismissing mental tortures or canceling these terms. We get 4. So, or maybe he meant it as a pun. I don't know. My daughter's studying Latin, so I'll have her take a look in 30 years. Okay, so that's the clue Euler got, and he would not drop something like this. How much time do I have left? Are we right on the hour about? 108? Okay, I'll try to get there. Okay, so we just write down these rules. I need to have them on the board. Actually, I'll just write the rule for multiplication. So I used to write this in algebraic order, but now that I discovered this, I'm going to write this in chronological order. I can't see any other order anymore. So, of course, and it wasn't just Euler who noticed this. Someone said, I'm looking at this, and I'm just seeing trigonometric formulas, trigonometric identities. Because I know that cosine of alpha plus beta is cosine of alpha times cosine of beta minus sine of alpha sine of beta. And sine of alpha plus beta is cosine of alpha sine of alpha, sine of alpha cosine of beta plus sine of beta cosine of alpha. Let me write this down. Those are the two identities, and you just see, oh, by God, these are just custom made to somehow take advantage of this. And the way you take advantage of this is you do this. You think of this complex number, and you multiply it by this complex number. And a few wonderful things happen. Look, at this point, we've suspended our dissatisfaction with the fact that this thing doesn't exist. And we're just playing this algebraic game. And now we kind of see what Euler meant. It exists in our imagination. So let's play with it. Why not? That's what we're doing. What this ends up equaling boy, what a beauty, isn't it? It's as if this rule, forget about minus 1, forget about square root of minus 1. It just seems like somebody wrote down a rule that's just had these identities in mind just so that this would work out. Just so that this would work out. Why is this beautiful? Well, this and this and this are 3 numbers all of the same form. Cosine of the angle plus, cosine of the angle plus I sine of the angle. They all have this form. We can give a name to this form. We can call it f of alpha. Do you know what Euler called it? You probably do. But I wouldn't have had this courage, but I would have called this f of alpha. Sure, I would have called this f of alpha. Although that didn't exist before Euler. 2 either. Euler introduced the concept of a function. He needed it for the differential calculus apparatus that he was developing. He needed it for calculus of variations, different story. But then you notice that this equals f of alpha. I'm sorry, this identity becomes f of alpha times f of beta, and that the result is f of alpha plus beta. That's basically acknowledging that these three numbers all have the same form. So I would have noticed this also. And then I also would have said, and you would too, that this is what the exponential function, this is the property that an exponential function, the exponential function satisfies. Remember? That a to the power of m plus n equals a to the power of m times a to the power of n, or e to the x plus y equals e to the x times e to the y. You guys are with me? So of course this looks like an exponential. So what would I call it? Let's think about what I would have called it, or you would have called it, if you just discovered it. Well, could you call it a to the alpha? No, because that already means something else. If alpha equals 2 and a is 5, 5 to the 2 is 25. It's not this. It's not this. So you can't call it a to the alpha. You can't call it e to the alpha. That's just the different, ooh. You can't call it that. That's taken. So what would you have called it? So I would have called it, I would have called it star to the alpha, and I would have been really proud of myself. Because look, all I did was introduce a new symbol, and now I can use this just as any other exponential, and you will see that already makes a lot of trig much simpler. Eagles. You can discover the formula for the triple angle, lots of things become much easier. This little invention would have simplified trigonometry quite a bit, and would have almost, this invention alone, this observation, would have made, and the fact that numbers of this form a field, which means you can multiply them, find the reciprocal, do whatever it is that you do with real numbers, would have been already a pretty good invention. Very nice, very neat. There are lots of tricks like this that, oh, it looks complicated, but if you do that, it looks simple. That's why that would have been very nice. Euler said e to the I alpha. If you first see this, it's like, that's just outrageous. That's outrageous, because when we see something like this, we are in the habit of doing certain things with this kind of symbol, right? We would know and have lots of expectations. First of all, we would expect that e to I alpha times e to I beta equals e to I times alpha plus beta. That would be our first expectation. Oh, well, gee, that works. Okay, fine, I'll give you that, Leonard. That works, okay. It's still obnoxious, though, because I also like taking derivatives of functions. That's what I do. And if I look at this, then I would expect, if you're, what's the right word, bold enough to give the symbol, then I would expect that this would be true, right? I know the chain rule, right? That this would be the derivative of e to I alpha. Right? Let me write down, let me replace this. Can I? Yeah, I guess. E to I alpha. I would expect that if I were to take the derivative of this, I would get this, right? By the chain rule, you guys are with me? No way would that work, right? Well, let's try it. If this is e to I alpha, then its derivative equals the derivative of this, and so it's minus sine alpha plus I cosine alpha. That's this. Is that the same as I times the original expression, cosine alpha plus I sine alpha? Yeah, it works. Okay, but wait a second. There's other things that we expect of this symbol in the time of Euler. Here's another thing that we expected of that symbol. And there's no way that works. Here's what we would expect. Here's what we know, that e to the x. People knew this before Euler, I believe. I don't know how far to go. Right? There's this. Right? If you're bold enough to introduce this notation, then there's no way that if I were to plug in I alpha here, I can also plug in I alpha here. Right? Just think of what would happen. E to the alpha, if this doesn't work, the whole notation falls apart. Well, let's see what happens. Let me collect terms right away. This would be 1. The next real one would come from this, right? I alpha, except it'll pick up a minus sign. So it'll be minus 1/2 alpha squared. Then the next one will be this. It'll come with a positive. So it will be, I'll put a factorial. It'll be plus 1/4 factorial alpha to the 4th minus, I can see the pattern, minus 1/6 factorial alpha to the 6th and so forth. And then when I combine the terms with I will get from here, I will get alpha. From here, I will get minus 1/3 factorial alpha cubed plus 1/, I see the pattern, alpha to the 5th and so forth. Okay? And then you're telling me, are you telling me that this equals cosine alpha plus I sine alpha? If that's the case, then this is the series for cosine alpha, and this is the series for sine alpha. And it's true. Right? So he saw that too. Foresaw that, right? So all of that went into this notation, went into this. This could have been, sorry, where am I? You know what I'm talking about, the Euler formula. This could have been easily missed, was it not for one great man. Okay, so he saw that too. That works also. That's what makes this such a brilliant invention. That's what made this such a brilliant invention, because it just united everything. Here, in one fell swoop, he united exponentials with sines and cosines. And so, I'll just mention it. Now that we're doing ODEs, and our recipe is solve the characteristic equation. Let's talk about second order ODEs. So we're solving equations of this kind. We're solving equations of this kind. Our recipe is write the corresponding characteristic equation. That's the associated characteristic equation. Solve it. Then the general solution equals. That's our recipe. If the roots are distinct and real. But with the help of this formula, you'll need to expand it a little bit more. You would have to have I alpha plus beta. This would need to be a little bit extended. Right? This recipe works. And we'll use it this way. Instead of now needing 2 recipes at least, you now still only need 1. Because when your roots are complex, this will become e to I some power. That's not legit. Because the final answer needs to be a real function. This is a real problem. The final answer needs to be a real function, just like we discussed with negative numbers and everything. Right? But this is an intermediate answer. You still have to match the boundary, the initial conditions. Solve for C1 and C2. They'll turn out to be complex. And then you put it all together, and the answer will be. And so this ties us back to the thing I said earlier. That if you solve a quadratic equation and get complex answers, that's just another way of saying that there are no solutions. This totally changes that statement, because this tells you shows you how to go from these non-solutions, how to take it further, get through it, and end up with a perfectly real answer without any additional work and any additional complexity. So that's this beautiful application right here. So, and that's relevant to this class, and then the Fourier series and all the other things we discuss. So just like that, it feels like just by the length of our discussion, we didn't do justice to the Euler formula. Well, let me just mention one more thing. That when you plug in pi for alpha, you get e to I pi equals -1. Or, as people love to write it, e to I pi plus 1 equals 0. And then what's commonly said, and I kind of buy into this, that if you think of what are the 5 most important numbers in mathematics, you would have to agree that it's 0 and 1, and e and pi, and I. And this relates all of them together. So that's a matter of taste. You have to learn taste from this mathematician. That's taste in its highest form. In my mind, there are 3 people who've achieved this level, and that's Archimedes, Newton, and Euler. I think I have 20 minutes left. I'm going to prove to you the fundamental theorem of algebra. You can write any number in polar form. Again, this is a broad overview discussion. I'm not going to talk about, there are lots of details to discuss. But you know that x plus iy can be written in the form r times e to I alpha. Hey, I missed the whole thing about square roots, but that's okay. We'll save that for later. Where r is the square root of x squared plus y squared. And alpha, well, I'll just write that tan alpha is y over x. Not only that, but you know, you can basically get exactly alpha back. Not just subject to pi, but exact alpha, because you have both x and y. Okay? And so when you multiply 2 numbers, so now if we have z1, which is the letter that's often used for complex numbers, that equals r1 times e to I alpha 1, and z2 that equals r2 times e to I alpha 2, then when you multiply them together, their r's, they're called absolute value or modulus, multiply, times e to I alpha 1 plus alpha 2. And of course, it's this form that's the key to taking square roots and cubic roots of a number, because that's easy to invert. Because when you cube a number, its radius or modulus cubes and its angle triples. So you can undo that by taking the cubic root of the modulus and dividing the angle by 3. And that's the key to taking cubic roots, which is something that you can't do with square root of 5. The whole discussion with the square root of 5 didn't have this beauty about it. So you couldn't do much with it. I think the term is that they weren't algebraically complete. There's a good term for all of this. Okay, so let's think about z and z squared. And here's what I want you to imagine. That z, which equals r times e to I alpha, and this would equal r squared times e to I 2 alpha. I guess I can write it like this, or 2I alpha. If we think of alpha as the parameter, and alpha is the parameter, and the real and imaginary parts of the result as the x and y coordinates in the plane, then this represents a curve. So we're going to treat the real part as the x coordinate, the imaginary part as the y coordinate, and alpha as the parameter. And so the corresponding curve will start here. Watch carefully, you have to see this dynamically. And it'll do this. Hey, that's pretty good. You guys agree? It'll just be one revolution. What does z squared look like if you interpret it the same way? Alpha is the parameter. The real and imaginary parts are x and y coordinates. Well, by the time alpha reaches pi, you've already traveled the full circle. So it will do this. This is going to pi, and this is going to 2 pi. So it'll go around twice. And z to the n, which actually equals r to the n, e to I n alpha, will go around n times. There you go. You guys are with me? And of course, r is a parameter. So if r is 1, all of these are unit length. But if r is 2, then this is radius 2, this would be radius 4, this would be radius 2 to the n. Okay? Now here's an interesting question. I'll show you in the video, I'll include it in the animation. What if you consider the function t? So at t equals 0, this just equals z, so it's just one circle. At t equals 1, it will morph from this function into this function. You guys are with me? So it will somehow morph from a single revolution to a double revolution, right? So if I were to do this and just pull the lever, and it goes from being this curve, which is 1 revolution, to being this curve, which is 2 revolutions. How does it happen? Well, I actually took a look at it, and I'll share it with you. But after a little bit of time, this develops a kink like this, right? That's for t equals something small positive. Then at its next most of time, it does this. This develops into a little loop. And then as you drag your lever to t equals 1, so z slowly becomes z squared, this little loop grows, and it becomes a circle, and it becomes 1, 2. Okay? That's kind of nice to see that. And now, if I have 5 minutes, do I? Do I have 10? 17. Oh my God, I'm going to milk this. And I will now prove to you the fundamental theorem of algebra. And its statement is the following, that any polynomial of the nth degree, we're now writing it with z because it's in complex variables. So it's going to look like this. I will call this a sub n minus 1, z to n minus 1, and so on until we get to a2 z squared plus a1 z plus a0 equals 0. This is our nth order polynomial equation. I will assume for the hell of it that a0 is not 0, because that would be just a special case. I would, if that was the case, I would factor out z and just deal with whatever's inside. So that's not a material assumption. But we're entirely in the complex world. All of our coefficients are complex as well. Statement. And again, this will be such a short proof and so simple and just amazing. Okay. Statement. This polynomial has exactly n roots, and I will actually prove that it has exactly n roots. Can you imagine that this can be done in 5 minutes? I just want to create this suspense. That right now, none of you knows how to prove this theorem. You may have taken complex analysis, and there it came out of, extremely sophisticated arguments. Right? Euler proved this in a different way. His argument is extraordinarily beautiful. This, based on continuity, this will also have continuity in it, continuity intuition. but right now, none of you know this argument. And in 5 minutes, all of you will know this argument and just how basic this theorem is. So here's our curve. Okay, suppose A0, right? We're in the complex plane, so this is A0. And we're looking for our solution Z in the polar form. And I will show you right now that there are n different r's and n different alphas, all corresponding to each other. So n pairs of r and alpha that satisfy that equals 0. So here's what we're going to do. I'm not actually going to write it, but here's what I'm doing. I'm taking this expression for z, this form of z, and I'm plugging it into this identity. Into that equation. I'm plugging it into that equation, and I'm looking for r and alpha. And at first, I'm taking my r to be tiny, like 1,000, 1 over 1,000, 1 over a million if you want. Let's see what the corresponding curve is, right? We already have some experience with what these curves look like. But when r is a tiny, tiny number, what does the corresponding curve look like? So we know what this looks like when it's just z. We know what it looks like when it's just z squared. We kind of know about this combination. We know what happens when it's z to the n. It's just n rotations that I erased. 1, 2, 3, 4, n. That's what it looks like. Okay, but when z is tiny, A0 is right here, but everything else is small, right? So this is small because r is tiny, right? And all of these other terms are even smaller. So I'll bet you that the curve basically looks like a tiny little circle, one revolution, right? Because you can ignore what these guys are doing. They can't do anything compared to this, right? Because z has absolute value 1 over a million. That's what we're going to see. So this is a circle of radius 1/1,000,000th times the absolute value of A1. That's really what it is. If A1 is 3, then this is a circle with 3 millions. Right? Now what I'm going to do is make r grow. Make r grow. And as r grows, these terms begin to come in and be much more significant. Now r will be 1 over 1,000. This would still dominate. But then I'll make it 1 over 100. Then I'll make it 1/10. Then I'll make it 1. Then I'll make it 10. Then I'll make it 1,000. So without first going to the final point right away, let's just say that when this term begins to dominate this one, right, we'll start seeing this, just like we did over there, right? So things grow because r is growing, but they also start doing this, and then it'll do this as it's growing, right? And then this term, the z cubed term, will come in and start dominating everything. And it'll form another loop somewhere, and now it will essentially go around 3 times as it's deforming. It's evolving. This basically provides all of the intuition you need for imagining how it evolves. But as the terms come into their own, remember, it needs to go from just 1 revolution around the circle to n revolutions around the circle. And now, so it'll deform as these terms come in. There are more loops. But let's think about what happens when r is 1,000. Now I want you to go to that. I want you to go from a tiny r, and we're here, to r equals 1,000. When r equals 1,000, all that matters is this term. Everything else has paled in comparison. So when r equals 1,000, and this will not be to scale, but it will be the essence. It will look like this. 1, 2, 3, 4, n. That's what it'll look when r is large. So look what happened. It all used to be in the first quadrant where I drew it, and then it continuously evolved to this, where there are n lines on the other side. So at some point it was like this, then it was like this, then it was like this, and now watch this. Then it was like this. I don't know how many times, but it had to go through the origin. right? If there were no loops, if the origin initially was outside of everything, and now it's inside n loops, then it must have, in the course of evolution, gone through the origin exactly n times. And every time it goes through the origin, that means there is a value of r and there's a value of alpha, where this expression equals 0. That passage through the origin constitutes a root of this polynomial equation. So on the path from r equals 1 millionth to r equals 1 million, it passed through the origin n times. And those are your n roots. And that's the proof. What do you guys think? Isn't it beautiful? And by the way, all you had to prove is that there is one root. Because if there's one root, there's Descartes' theorem that says that you can factor it out. And then you're left with a polynomial equation of one order less. And then you just prove, and then by the same token, you prove that it has one root, and the next one has one root, and so forth. And so you only really need algebraically to prove that there is one root. But this continuity argument shows that there are n roots. And so that's it. So I think everything I wanted to say, we didn't discuss square roots and all of that wonderful business. And this paradox, that I squared equals minus 1, but I times I is the square root of minus 1 times the square root of minus 1 times the square root of minus 1 times minus 1 equals square root of 1 equals 1. So minus 1 equals 1, which I wrote out on the board. And then having thought about it for a long time, I believe that the problematic equal sign is this, not this. You can make sense of this. You can interpret this as being correct. But this is where it fails. So you can't apply the square root to 1. Okay, so everything I already said, everything I intended to say I already said, so I'm not going to repeat it. I wish I could give this a rousing finale, but I can't, so there you go. Complex numbers, I hope you enjoyed it.